Hi, and welcome back to DATQVAULT video lectures. In this video, we're going to cover the topic of resonance. In organic chemistry, it's a really simple topic, but it's a really important topic that spans across many other topics in organic chemistry. Um, just remember that there are 30 questions on the organic chemistry portion of the DAT. So for each of the topics we cover in these videos, you're really only likely to see one or at most two of those types of problems on the DAT. But for topics like resonance, it really plays a role in many organic chemistry topics, like I said before, such as acid-base chemistry and ortho-para-directors of like reactions like electrophilic aromatic substitution. So it's important to have a firm grasp on topics like this one. And remember, getting one extra question right on the DAT can really make a huge difference. So remember to study hard and try to grasp the simpler topics and the more important topics like resonance. So the definition of resonance is two or more Lewis structures that can be drawn for a single organic molecule. I'm going to go over three major rules of resonance structures to help you figure out A, if you've drawn a resonance structure correctly, and B, if one resonance structure is favored over another resonance structure. So the first rule we're going to look at is atom connectivity remains the same in all resonance structures of a single molecule. The next rule we're going to take a look at is contributing structures, which is just a fancier term for resonance structures, must have the same net charge and number of electrons. And the last rule we're going to look at is resonance structures with the largest number of formal charges are typically the least stable of the resonance structures for that molecule. So let's look at the first rule. Atom connectivity remains the same in all resonance structures. So for these rules, we're going to use a simple molecule, carbon dioxide. So let's first learn how to draw a resonance structure for carbon dioxide. And when we go to draw this resonance structure, we're going to try to keep the atom connectivity the same. So we can take some electrons from this double bond, two of these electrons, and we can actually move them onto the oxygen atom. So we're taking one of the electrons away from carbon in this bond, and we're giving it completely to the oxygen atom. This gives us this resonance structure over here on the right, where carbon, since we're losing an electron from it, now has a positive charge, and the electrons in this double bond are going completely to oxygen. Now oxygen is going to have a negative charge. Resonance structures are denoted by a double-sided arrow. So notice in this structure, carbon is still connected to both oxygen atoms, and in the structure on the left, carbon is still connected to both oxygen atoms. So this follows the first rule of resonance structures, atom connectivity remaining the same. Let's look at this structure down here, this amide molecule. There are many resonance structures that you can draw for this amide molecule, and I suggest you actually try to draw them. But for this example right here, I'm going to give you an example that is not a resonance structure of this amide molecule. Here we have the structure on the right hand side where we have taken this hydrogen from this amide NH, we've broken the bond, and we've placed the hydrogen or this proton up on oxygen. We've taken the pair of electrons from this NH and we've put them into this carbon-nitrogen bond. Notice this is not a resonance structure because we've changed the connectivity of the atoms in the molecule. We've broken the connection between nitrogen and hydrogen, and now we've made a connection between oxygen and hydrogen. These are not resonance structures, so we cannot draw the resonance arrow. These structures are actually what are called tautomers of each other, and this reaction right here is called tautomerization. Alright, so tautomers are molecules where you take a proton and you basically transfer it to another atom in the molecule and you gain a double bond. Alright, let's look at the second rule of resonance structures, and that are contributing structures must have the same net charge and number of electrons. So let's go back to our old friend carbon dioxide. Again, to get this resonance structure on the right-hand side, we're taking 2 electrons out of this carbon-oxygen double bond, and we're giving them all to oxygen, leaving us with a positive charge on carbon, a negative charge on oxygen, and an extra lone pair of electrons now on oxygen. So first let's see if both of these molecules have the same net charge. And how do we do that? We just look and see if each of these atoms in this molecule have a charge. On the structure on the left, all these atoms, have a charge of 0. In this molecule on the right, carbon has a charge of +1, oxygen has a charge of -1. So the net charge when adding these two charges together in this molecule equals 0. So the net charge for both of these molecules is essentially 0. So one of the rules is now satisfied for this overall second rule of between contributing structures. So the second rule we're going to look at is that these structures have the same number of electrons. So it's simple to do that. We just count up the number of electrons in each of these molecules. These oxygens together bear 8 lone pair electrons, and there are 8 electrons altogether in these set of double bonds. So together there are 16 electrons in the structure on the right. Number of electrons in the structure on the right hand side over here, we again have oxygen this time bearing 10 lone pair electrons. There is 1 double bond and 1 single bond, so that adds up again to 16 overall electrons in the structure. So both the connectivity is staying the same between these molecules. They both have the same net charge, and they both have the same number of electrons. So that really satisfies all the rules to determine if these two structures are resonance structures of one another. Let's take a look at formaldehyde. You can actually draw a resonance structure of formaldehyde by, again, taking some electrons out of this carbon-oxygen double bond and putting them onto oxygen, just like we did for carbon dioxide. That gives us this resonance structure over here on the right. Oxygen has a negative charge, and carbon has a positive charge on it now. So let's go through all the rules to figure out if these are truly resonance structures of one another. We are keeping the same atom connectivity. Carbon is connected to 2 hydrogens and oxygen. Over here on the right, carbon is connected to 2 hydrogens and an oxygen. The second rule, we need to satisfy the net charge rule. Here we have a net charge of 0, and here we have a positive charge of 1 and a negative charge of 1, which overall gives us a net charge of 0. So both of these molecules have a 0 net charge. Number of electrons in each molecule, we can count them up. We have 8 electrons up here between the oxygen lone pair and the carbon double bond, 2 electrons in this carbon-hydrogen bond, and 2 electrons in this carbon-hydrogen bond. So we have overall 12 electrons. In this molecule over to the right, you will find that we also have 12 electrons. So these two structures are indeed resonance structures of one another. All right, let's look at the third rule now, which is more of a rule figuring out which resonance structures are most stable. This rule doesn't really contribute to figuring out if these two molecules are resonance structures of each other, but it's more based on stability. Let's look at carbon dioxide once again. And again, to get this resonance structure on the right, we're going to take a pair of electrons from this carbon-oxygen double bond and give them to oxygen. So now we need to figure out which of these structures has the largest number of formal charges. This oxygen in this structure has a formal charge of 0, this carbon has a formal charge of 0, and this oxygen has a formal charge of 0. How do we figure out how to calculate a formal charge? If you guys forgot how to do that, I'll go over it really quickly. Formal charge on a particular atom in a molecule is based on the number of valence electrons of that atom minus the number of lone pair electrons on that atom minus the number of shared electrons in that atom divided by 2. So let's take a look at oxygen in the case in the left-hand side molecule here. Oxygen has 6 valence electrons. It has 4 lone pair electrons. There are 4 electrons shared in this carbon-oxygen double bond, so that's 4 divided by 2. This overall gives us a formal charge of 0 on this oxygen. Alright, let's look over here on the right. This carbon has a positive charge on it. By writing a positive charge on this carbon, we're denoting that it actually has a formal charge of 1. Oxygen has a negative charge, so it has a formal charge of negative 1. But we can actually calculate this out using the equation down here. So let's do it for carbon in this instance. Carbon has 4 valence electrons. The number of lone pair of electrons on this carbon atom is 0. And now I have to subtract the number of shared electrons. There are 4 shared electrons in this carbon-oxygen double bond, and there are 2 shared electrons in this bond. So that's 6 total electrons divided by 2, which gives us a formal charge of +1 on this carbon atom. Since this CO2 molecule resonance structure has the most amount of formal charges in the overall molecule, this molecule is going to be the least stable of these 2 resonance structures. Alright, here's a practice problem for you guys to solve really quick. I want you to draw all the resonance structures for this furan molecule. So go ahead, try to draw all the resonance structures that you know how for this molecule, and then we'll go over it together. Alright, let's draw all the possible resonance structures for this furan molecule. Remember that resonance structures are denoted by a double-sided arrow. We can take a lone pair of electrons from this oxygen and put them into this carbon-oxygen bond. And then we can take this carbon-carbon double bond and take 2 of the electrons out of it and put it onto this carbon atom. If we do this, it satisfies all of the rules for resonance structures. And we get this structure right here, which is a viable resonance structure of this furan molecule. We can draw another resonance structure by taking these electrons on this carbon, putting them into this carbon-carbon bond, and taking this double bond and putting 2 of the electrons onto this carbon. If we do this, we get this resonance structure. We can keep working our way around this molecule by taking these electrons here, putting them into this bond. Oxygen still has a positive charge on it, and taking the electrons in this double bond and putting them on to this carbon. Notice oxygen still has a positive charge in each case, and we're moving around these electrons or this negative charge onto each of the carbons in this cyclic molecule. There's one last resonance structure that we can draw. We can put these electrons into this bond, move these electrons onto this carbon, Alright, and then we can actually get back to this structure up here by taking this electrons in this negative charge, putting them into this bond, and then putting the electrons back onto oxygen. And we can get back to the starting furan molecule. So there are 4 different resonance structures that you can draw for this furan molecule. This is a really good exercise. And so to draw this out, you can count the formal charges. You can make sure that none of the atoms have actually shifted. And you'll see that these are all viable resonance structures for this furan molecule. Alright, let's end with doing a DAT style question. So which molecule is not a resonance structure of the others? So of course 4 of these molecules are going to be resonance structures. One of them is not a resonance structure of the others. So why don't you pause this video for a second, try to answer this question, and then we'll solve it together. Alright, now that you've had a chance to solve this question, let's go over it together. There are a couple different ways you could actually approach this problem. One of them will take a lot longer than the other, so you can actually pick out one of these molecules and draw all the resonance structures that you know of for it and figure out which one doesn't match up. Or we can go and look at or try to remember all the rules for resonance structures and figure out which one doesn't really match up. The rule that comes to mind for me is rule number 1, and that is Have we broken any of the connectivity in the molecule for any of these resonance structures? So let's look at the first one. Here we have a positive charge on nitrogen and a negative charge on this carbon. It seems like it could be a resonance structure. So let's compare it to molecule B now. If we notice in molecule B, we've actually broken connectivity. We've broken one of these nitrogen-hydrogen bonds, and we've created an oxygen-hydrogen bond. So we've completely broken connectivity. So A and B are definitely not resonance structures of one another. Now let's compare B and C. If we compare B and C, we also notice that we've broken a nitrogen-hydrogen bond and we've created an oxygen-hydrogen bond. So B and C are definitely not resonance structures of one another. Let's go and check A and C and see if they're resonance structures of one another. We haven't broken any connectivity between any of the bonds in the molecule. Everything remains the same formal charge. We can actually push electrons to draw the resonance structures, and we'll find out that A and C are definitely resonance structures of one another because of everything that I've listed. You're not able to draw on the test, but I'll show you how these are resonance structures. You can take these electrons here, put them into this carbon-carbon bond, move these electrons into this bond, and move the electrons here up onto oxygen, and you'll get structure C from structure A. You can do the same thing for D and E. So we find out that B is definitely the outlier just using the first rule to pick out that B is definitely not a resonance structure of either A or B. We don't even need to really compare A and C because we've already figured out that B is not a resonance structure of either A or C. So that's the quickest way to pick out that B is definitely the outlier here and cannot be a resonance structure of any of these other four molecules. Alright, hope you learned a lot from this lecture. Remember that there are test questions that you can take relating to this particular topic to solidify everything you've learned in this lecture, and we'll see you back here for another DATQVAULT video lecture.